Okay, so this there is the circuit, and okay, so I'll just leave it there. Now, so our idea here is, look, we got a three-phase source here, and it's Y connected. And even though we're told that it's a three-phase 440 volt 60 hertz source, we're supposed to interpret this 440 here as a line voltage. So I haven't indicated a phase voltage on here. I've indicated that that is a line voltage. We're told we have a 30 ohm resistor and a 40 ohm inductive reactance in each phase. So 40 ohm inductive reactance, then we got 30 ohms for the resistance, 40 ohms for the inductive reactance. That three-phase load is connected in Y, and we have to consider it to be balanced, so we got that 30 ohms and 40 ohms in each phase. Now, we haven't shown a neutral connection. We haven't shown a phase voltage, but we're going to calculate it. So one of the things we can think about is that, this is the phase voltage here. And if we connected a neutral, we could show it there. And one thing about connecting neutral is that in some three-phase circuits, especially these Y-Y connected ones, we could take out a single phase and analyze that, and sometimes that becomes easier. And so my cursor's a dot, sometimes I lose it, but if we took out a single phase out of that, we got V phase here, which again we haven't calculated that yet, but we will in a minute. And here's the line, and whether you call, this up here, if we're considering phase A, then this would be phase A. And so then we're going across, we got our resistor, we got our inductor, and then down here, we got our neutral connection. And now, this kind of gives us now a phase current, right? But in a Y-connected system, phase current and line current are equal, because where the phase here turns into the line here at node A or point A, there's no current division. So I line got to be equal to I phase. And so we got our 30 ohm resistor, our 40 ohm inductance, and now your impedance triangle, right? 30, 40, and Z phase there, right? And so if you know Z phase, you can calculate I phase relatively easy, as long as you got V phase. And like I said, we'll calculate V phase now in a minute. And so R phase, and remember, inductive reactance is XL phase, right? And this here be theta, and this angle over here, of course, is a right angle. Now, so then let's think about part A. And I usually like to start off, I'll usually words on my three-phase questions like this, right? And so, because the 440 volts that we're given is the line voltage. And remember that really it references the source. But the line voltage is the same for the source and the load. The line current is the same for the source and the load. And so that's what connects the two. Okay, so for part A, again, we have to assume that, we have to assume that in the source, the voltage that we're given is V line. And so that is equal to 440 volts. Now, with respect to stuff we covered last class on ratings, that's what industry tells us to do. You goes to the nameplate, or you walks over to a panel, and that's a three-phase panel, and it tells you it's 440 volts. That's to be interpreted as line voltage. Okay, so now this is a Y system, and so in a Y system, we know that V phase is smaller than V line, and we know that the value that relates them is root 3. So that means V phase is V line divided by root 3. and that gives us then 440 volts divided by root 3, and that calculation comes out to be 254 volts. Now, and so therefore, if I was writing the number on the phase voltage here, it'd be 254. And so that makes that a, if you want to state it this way, which is also acceptable, 254 slash 440 volt system, where this is normally, considered to be the phase voltage and the line voltage. Okay, so now for part B then, we want to move on to the load, right, and think about our voltages. So again, what connects the load back to the source is the lines, and so V line 440 volts, got to be the same for both of them. So then, in order to come up with the phase voltage in the load, consider its connection. Well, it's also a Y connection. So that means that we don't need to do a calculation over there, because V phase again is 440 over root 3. And that's, wouldn't be true if it was a delta connected load, but because in the delta, V phase and V line are equal. So V phase in the load and in the source could be different. That's common if there's one's a Y and one's a delta. In any event, now we got 254 volts for this one. Okay, now for part C, we are asked to consider the load, and whether we consider the single phase up here, and I'll call that IPL, but I phase I meant to put there PH. Now, and so, oh yeah, maybe it was an H, I just didn't do it very neatly. In any event, now, in order for us to consider the source, if we're considering a line, Z line is not something down here that really we consider. So we got a 30 and a 40 with an angle in between them, theta L. We got another 30 and a 40 over there, and if we're going to try to add them together, remember there's a 120-degree angle right there, and so Z line is half complicated, and so really is Z phase that you want to do, and that comes from this impedance triangle right here, right? And so normally then, remember now that for part C over here, we're still considering the load. And the reason why we're considering the load is that, well, that's generally where you starts off your calculation of current, because, well, the current comes from the source is developed by the load, and so is the load always where we should start our current calculation, right? And so in the load, we want to start off by saying that Z phase, because that's a right angled triangle over there, is equal to the square root of R phase squared plus XL phase squared. And if you recall from, I suppose we call it trig, 3, 4, and 5 triangle, the 30, 40, 50 triangle is the same, right? So 30 squared plus 40 squared, take the square root, gives you 50. And so Z phase is equal to 50 ohms. And so now if you got Z phase and V phase, of course it's I phase that you're calculating. And so I phase in the load is equal to V phase in the load divided by Z phase in the load. And now your biggest issue is, did you remember to calculate Z phase instead of using just R? And so, remember now we're moving into the AC world, and the impedance of the circuit is the number that fits in Ohm's law. And so you got to calculate the impedance before you can find the current. And so here, remember now, Z phase was 254 volts, and Z phase 50 ohms. And so in the load, I phase is equal to 5.08 amps. Okay, so now for line current, we'll recall now that in a Y system, I line is equal to I phase, and so of course it is 5.08 amps. Part D now, and so I'm going to move up here. Part D now asks us to go back to the source. And so remember now that your procedure now is to consider that for both the source and the load, the line quantities are equal. So our line is 5.08 amps. And these Y-Y connections are really the easiest, because when we get back to considering it be a Y connection, we know that likewise what we said for the load, I phase equals I line, and so no change in the currents here. Our currents are equal, and so when there's no delta connection, that becomes well, hopefully straightforward. So 5.08 amps. My 8 are kind of missing. Okay, so now the tricky part of this now might be part E, and that is the total real power delivered, which again I like to call P3 phase. Now, the easiest way to do it for this particular question is to say P3 phase is equal to 3 times P1 phase. And the reason for that is that, the power delivered to the phase, again, if you go and think about this circuit here, is the power delivered to the resistor. And the easiest way to calculate that is I squared R. So, P1 phase is equal to the load. Now I'm thinking about doing this for the load, right? I phase in the load squared multiplied by V phase in the load. And we got there 5.08 amps squared and 30 ohms. And so P1 phase has a value of 774 watts. So P3 phase is equal to 3 times 774, and P3 phase, PT if you want to call it that, right, is equal to 2,322 watts. Now, yeah. For the voltage, 254 volts over, part E. Oh, yeah, okay, caught me there. And so now my calculation is correct there, right? That's just a typo there, right? Yeah, I put in 30 ohms, but no, right there. Look, my power is I squared R, and so I'm supposed to have R phase there. So the 30 ohms is correct, eh? Yeah, sorry about that. Yeah, and so this there should be R phase, and it is 30 ohms, right? I squared R for the power over there. Now, remember P equals IV, but see, when we says P equals IV, see, in a DC circuit, P equals IV, and we got to get away from that, because now S equals IV, and P is equal to S times the power factor. So P equals IV times cos theta, or IV times the power factor. And we got to be careful about that, because that's why I went this way to calculate P. And so let's think about that now. Because we said earlier that the equation that we should be using to calculate P three-phase is root 3 times V line times I line times the power factor. And, you know, that requires a bit more work from us than our 3 times I squared R, because we got root 3, and remember now we're generally doing this for the load. So V line in the load, well, V line is the same wherever you looks at it, right? 440 volts. And I line typically from the load is our 5.08 amps. But we need the power factor, and we don't have it. And so power factor, it's the load power factor. And so you got to go back to this triangle. And for that triangle, remember, theta is the inverse tangent of the vertical component divided by the horizontal component. And so we have then the inverse tangent of XL divided by R, which is 40 over 30. And if you work that out, theta comes out to be 53.13 degrees. And you can see this is a bit more work, right? Now, power factor then is cos theta. And so the cosine of 53.13 degrees gives you 0.6. And that's kind of an efficiency. What it tells you is that 60% of the apparent power delivered to that load is used as real power. The other 40% is wasted, right? And so, 60% of the power is real power. And I don't know if we can say 40% is wasted, because you'll find that because XL is bigger than R, QL is bigger than P. And so, there's, that's open to perhaps interpretation, but 0.6. And so now if we go back down to our power equation, 0.6 goes in here for the power factor. And if you work that number out, you come up there with P3 phase is equal to 2,300, and rounding here gives you 23 watts, which is basically the same number that we had here. But, again, a bit more work to calculate it using this equation, because you got to come up with the power factor there. And again, that comes from the load phase angle, which comes from the impedance triangle that we drew there. All right.